record. There we go. Right. So we're going to start with trig. Trig is a third of your paper. This is all on Google Classroom. And like I was saying, I've put 4 bits of past paper or 4 past paper questions all together for you guys per topic. Just because paper 2 is typically the harder or the paper everyone finds harder. So I've just put an extra paper in there for you guys. The memos are all there. This document that I sort of showed right at the start here. So the document that contains your breakdown is there as well. It's called your assessment policy. It's about a 20-page document as well, but it breaks down each section according to what you need to know. So for example, in trig, it's going to tell you need to know how to apply a reduction formula, how to solve a general equation, how to use trig on the Cartesian plane, how to do trig graphs, etc., etc., etc. So it gives you a very, very clear idea of what is expected of you in your papers. So it is something worth looking at. But let's have a look at our questions. Now the trig stuff, guys, remember it's sort of 3 parts to trig, I suppose we could call it. You've got general trig, which is the bulk of those 50 marks. About 30 to 35 of those marks is general trig. So if we have a look, okay, we'll get them, but it's the bulk of. So about 70% of the trig questions is just general trig. Can you solve an equation? Can you simplify? Can you use trig on the Cartesian plane, etc., etc. The other marks then come from your trig equations and your 3D trig. So trig equations, really not any different from grade 11. 3D trig, there's absolutely nothing new in terms of formulas that you need to know from grade 11. It's just now you have to visualize the image in 3 dimensions. But again, absolutely nothing new. So we're going to go through this. Depending on time, I might not do the trig equations or the 3D trig again, just because the bulk is this trig and then obviously the geometry and analytical. I say to you guys as well, if you are joining us for the actual lessons, that I might leave that. Well, I'm definitely going to leave analytical for the end because we're currently doing analytical, so it should be fresh in our minds. We are going to do past papers, so most of you looking at our list are doing the lessons anyways, so we're going to get to that analytical in any case. All right, but let's start with the trig. So guys, trig, if you have joined us for the lessons, there are 5 types of questions that I can ask you, or that you are going to be asked in trig rather. So the one is simplifying expressions. The second is working with trig on your Cartesian plane. Oh gosh. It's getting worse. I am going to get it fixed. I'm fully aware of the problem at hand. Simplifying the Cartesian plane. General solution or equations. Identities. You then have the 5th type of question, which is your complex problem solving type of questions, which again is using all your knowledge that you already have from essentially being able to do the first 4 types of questions and applying it to a 3D trig, a trig function, etc., etc. Right, so those are the 5 types of trig questions that you're going to get. We've already sort of focused on the 4 for those of you who were in trig lessons with me or during the trig course. So we're going to go through them all again and we're going to make sure that we're happy. So the first paper that we're going to go through, or the first question that we're going to go through, is from last year's final. So you'll see exactly what they were asked last year. And the first one starts with trig on the Cartesian plane. There's ways that I know this, but let's just read the question first and then I'll explain to you why we know that we're going to need to use a diagram in this question. So it says, given sine beta equals a third, where beta is equal to 90, where beta rather is an element of 90 to 270. So a couple of things I want to point out here. Firstly, it says, without using a calculator, determine each of the following. So the second we're told without a calculator, there's two things that should come to mind. One, special angles. But because the ratio that I've been given here does not have an angle, we're working in terms of beta. The second thing that should come to mind is, okay, I'm going to need to draw a diagram based on the information I have, using my ratio, using the restriction on beta, and I'm going to have to essentially use that diagram to answer my questions. Right, so because there's no angles, I know I'm not using spatial angles, I'm going to have to use a diagram. The second thing we need to be mindful of is this restriction on beta. So essentially it's giving me an idea of where on the Cartesian plane I'm going to work. So you might be thinking, geez, 3 marks or just writing down cos beta. That seems like a lot. Yes, but the reason it is a lot is because you have to draw a diagram, you're going to have to use Pythagoras to work out a missing side, and then get your ratio. So, excuse me, even though it doesn't say with use of diagram or using a diagram, whatever, you're going to need to draw one in order to help yourself. So if we now break down what we have here, what we've been given is sine beta equals positive a third. So automatically we know the ratio for sine is positive, which automatically means that I'm working either in quadrant 1 or quadrant 2. The second bit of information I was given, that beta is an element of 90 to 270. That is essentially eliminating or telling me to ignore quadrant 1 and quadrant 4. So here I'm actually only concerned with quadrant 2 and quadrant 3. Now, if we have a look at the overlap of where sine is positive and where or which quadrants I'm allowed to work in, the overlap between these two bits of information is quadrant 2. So in terms of my diagram, I'm going to draw it in quadrant 2 because that is where all of this information sort of comes together and all forms this diagram that I'm about to draw. So quadrant 2 is here. You've got your line segments. It's not a very good line. Let's try that again. Now, if you want to draw this as a triangle, that's absolutely fine. Some people do, some people don't. I prefer a triangle. I think it's easier to work with for my brain, but if you don't need a triangle, that's fine. It is a right angle triangle. Your angle measured from your positive x-axis is the angle in question, so beta. And we have been given a ratio of a third. So sine beta is equal to a third. And what you need to remember is that sine on your Cartesian plane is y over r. So you've been given the y value 1 over your radius, which is 3. The value that you do not know is x, and this is where Pythagoras comes in. So to work out this x length, I'm going to have to use Pythagoras. So x squared, oh gosh, sorry. Let's try again. X squared is equal to 3 squared minus 1 squared. Hypotenuse minus the other side. Remember your recent Pythag. And so we get that x is equal to, and you just type this on your calculator. If you want to go a step further, you could actually have said x is equal to then the square root of 3 squared minus 1 squared. Completely up to you, whatever you're more comfortable with. But essentially you get 2 square root 2. Now what's really important, grade 12s, is that you double check your diagram, you double check the quadrant you're in, and you double check what sign your x and your y value should be. So my y value is a positive 1 because it's above my x-axis, it's a positive y value. But if we look at where we are in the Cartesian plane in terms of x is negative. So this length for x that I have just determined is negative 2 square root 2. If you want to leave it as square root 8, that is obviously absolutely fine. There's nothing wrong with that. I've just simplified it as much as I can, but it really doesn't matter. Okay, so you have to use Pythagoras in order to find out your missing side. It's generally either going to be x or y, unless we give you tan, then you would be finding your radius or your hypotenuse. And always double check back onto your quadrant whether or not it should be positive or negative. Now this makes sense. Cos, which we're about to find, on your Cartesian plane is x over r. But in quadrant 2, cos is negative. So there should be a negative value that I'm about to use to find this ratio. Right, now that I have got all of the information I can possibly get, from the information given to me, I can go work out cos beta. So cos beta, exactly as I've just said, is x over r. You've just worked out x to be negative 2 root 2, and your radius was 3. That's it. Okay, full apparently the arrows can go the other way. That is it. That is all you have to do. That's all that's required of you. You have gone and worked out your ratio. So the first one is generally nice and easy, a nice tan beta, cos beta, depending what you're given. And then it starts to step up in complexity where we introduce maybe double angles, compound angles, reductions, co-ratios. And so now that we have this information, it's going to be useful in our next step. So in the next question, we have been asked to find tan of 2 beta. Now, bear in mind, the angle that we are working with, or the angle that we were given in the question, was just beta, not 2 beta. So no, you cannot just double a ratio. Can you see? Yeah, I'll do that now. Sorry. I'm just like on the trig train here. I will show you the mark allocation now. I did explain it earlier, but I will explain it again. But guys, the second there's a double angle, an angle that is not given to you in the question, you need to start thinking about the formulas you know from your formula sheet. Okay, so can you see this question quickly? What is your mark allocation? So you're going to get a mark for doing Pythagoras because you have to go and work out that x length. You're going to get a mark for understanding that x is negative 2 root 2. And then you get a final mark for your ratio for cos beta. So that's what I said earlier. You have to do Pythagoras. You have to get your x value or whatever value you're working with, and then you're able to get your ratio. So that's the 3 marks that you get. All right, so 5.1.2, what do we think we're going to do? I'll put in the chat, you can raise your hand. How am I going to deal with the sine 2 beta? I said raise your hand, you can just unmute yourself. Pomelo, awesome, exactly, a sine double angle. Now, a sine double angle is 2 sine theta cos theta. Remember, you do get given a formula sheet, and I have put a formula sheet on Google Classroom for you guys. So this is our double angle expansion. Now, if you think about what we've done and what we were given, sine beta was given to us in the question, and we've just worked out cos beta. We have all of the information that we need to go and work this question out. So sine beta was given to us, that's a third. And cos beta was given, well, we've just worked out negative 2 root 2 over 3. Now, it does say without a calculator, and so if you're feeling particularly fancy, go for it. Go work this out without a calculator. But it's not really necessary. There's no need to try and do it without a calculator. Just type it into your calculator. So yeah, my advice, once you substitute it in, what we care about seeing, and you'll see now in the mark allocation, what we care about seeing is that you've understood the double angle, that you were able to substitute the appropriate formulas, but then the final mark is just your answer. So by all means, if you want to try and do this in your head or sort of by hand, go for it. But I would just type this into a calculator. So in doing exactly that, or doing it in your head, whatever your heart desires, you end up with negative 4 root 2 over 9. So here, what we're looking for is your expansion of the double angle, your substitution, and then your final answer. That is where you get your 3 marks from for this question. And that's what I was saying earlier. We now start to build up the complexity, asking double angles, compound angles, etc., etc. Okay, so if we now look at 5.1.3, we've got cos of 450 minus beta. Now, there's a couple different ways that you can deal with this question. Excuse me. A couple different ways that you can deal with this question. It is entirely up to you, and it's entirely based on what you see. All right, so I know the way I would do it because I think it's easier, but that's not to say it's the only way to do it. So have a look at this and tell me what you guys think we can do for this 5.1.3 here. Shumelo?
Ma'am, could we start by reducing and then using like a double angle, or not double angle, a compound angle?
Okay, awesome. So when you say reducing, what is making you say that?
Ma'am, it's over 360 degrees, so we'd use the reduction formula.
Awesome, exactly. So guys, remember, anytime you're given an angle over 360, you can add or subtract 360 as many times as you want. You still get the same angle. The reason for that is because 360 is a circle. So if this is your angle beta over here, if you add 360, you end up at the same place, just 360 degrees later. If you subtract 360, you end up at the same place, just 360 degrees earlier. So you need to remember that in the back of your mind, because if you do that with this question, it makes it so much easier. You definitely can use compound angles. So if you see this immediately as a compound angle and you expand it to cos 450 cos beta plus sine 450 sine beta, that's fine. You're just going to do that reduction twice for the cos 450 sine 450. Makes no difference. But I would do exactly what Camilo said here. And I'm going to add or subtract the 360. So 450, I don't know what I'm doing here. 450 minus 360 is 90. So you end up with cos 90 minus, and Lumelo's just sent me a message to confirm exactly this. Alarm bells, it is a co-ratio. Cos 90 minus is sine beta, and you were given this in your question. You don't even have to go look at your diagram. You don't have to do anything. You've got the co-ratio, you've got sine of beta, you know what the ratio is. So like I say, if you didn't want to do that and you had seen the compound angle and you had expanded this to cos 450 cos beta plus sine 450 sine beta, that's absolutely fine, because what's going to happen is, again, according to that reduction Camilo mentioned earlier, this becomes cos 90 cos beta plus sine 90 times sine beta. And remember, 90 is actually a special angle. So both of those annexations. So because it is special angles, you need to be very careful about what you're working with here. Now cos 90 is 0, so 0 times cos beta is actually gone, and sine 90 is 1, so you're actually just left with sine beta, which gives you a third. So it makes no difference how you choose to do this. It makes no difference what you're seeing. As long as you apply your trig rules, your trig identities, your trig formulae correctly, you're going to get it right. So some people might automatically think, cool, compound angle formula, let's go for it. Gives you exactly the same answer. All right, so never doubt yourself. Often when you guys are going through past papers, just bear in mind they do give alternate memos. So if your first memo doesn't match up with your answer, double check that there isn't an alternate memo for a different way that you can complete the question, particularly for trig, geometry, both analytical and Euclidean. Those are generally the ones where there's a lot of alternate memos. Paper 1 is generally quite straightforward, but I mean, that's not to say there aren't other ways to do a question. Right, so for this one, in terms of your mark allocation, depends obviously how you choose to do it. It would still be 3 marks either way. So what you guys need to remember as well is that just because your method is different doesn't mean you lose marks because you've used a different method. If your method is different, but still mathematically correct, you'll get all 3 marks. So for the first one, it would be that reduction, so subtracting 360, understanding the co-ratio, and then getting a third. For the second one, it would be your expansion. It would be applying the reductions of the cos 90 and the sine 90. Essentially just getting a sine beta. And then a final mark, obviously, for your answer of a third. Okay, so these sort of questions, what I need you guys to realize is that these are, let's not say the easy questions, but these are the questions where you can start banking your trig marks. Right, there's definitely going to be harder questions as we go along, but this is where you bank your marks because you've got a diagram, you have the formula sheet in front of you. This is where you can get, I mean, this is 9 easy marks that you can bank immediately. Question 1 of trig, you've got it sorted. Okay, so let's take a screenshot of that and then we'll move on to the next one, which is having a look at an identity and some different questions that we can ask you around identities. And remember, guys, if you've got questions as I go along, please just ask. Okay. So if we have a look at this next question, 5.2, like I say, this is an identity. So we have been given cos to the power 4x plus sine squared x times cos squared x plus, no, divided by 1 plus sine x. So the first question is asking us to prove that that whole fraction is equal to 1 minus sine x. So it's asking us to prove an identity. Now, again, and I said this to you guys before in class, there are lots of different ways to prove an identity. It's going to very much depend on sort of what you see first and what you're able to apply in the context. But there's lots of different ways to prove that this fraction is equal to 1 minus sine x. So very much dependent on what you see. The first thing that we need to decide, though, is which side of this identity we're going to manipulate. Now, this one is fairly obvious because there's a heck of a lot going on the left-hand side and not a whole lot going on the right-hand side. But things to look out for in terms of deciding which side to manipulate. Look out for tan, because tan we have an identity for. Look out for your double angles. Look out for a situation where you can maybe factorize through dots, highest common factor, quadratic. And look out for things like maybe being able to find an LCD. So those are just some things to look out for. Generally speaking, though, you can sort of see which side to manipulate. But if you're not sure, like I say, start with the one that looks busier or a little more complex. And at the end of the day, guys, manipulate both sides. Because at the end of the day, if the left is equal to the right, you manipulating both sides will eventually get to a point where they're both equal. So those are the 4 things that sort of to look out for that we generally throw to you. I'll say them again. Look out for tan, look out for double angles, look out for factorization, and look out for an LCD. But when in doubt, start with the more complex side. You can always manipulate the other side as well. But always start with the thing or the side that has more going on with it. So we're definitely going to be manipulating the left-hand side here. Right, now, when doing or when proving an identity, you do need to state which side it is that you're working with. Because remember, we don't work with this as an equation. So it's not like I'm going to bring the sine x over and make it plus sine x. No, we keep the left and that right separate and we work with them separately. So based on the 4 things that I've said we need to look out for, who can give me something that I could maybe do here? We've got cos to the power 4x plus sine squared x cos squared x over 1 plus sine x. What could we do? Say the 4 things again. No, I won't, because Shlomilo's on it. Right, in our numerator, I forgot the word there for a second, we have got a highest common factor. Right, there was also a suggestion of we can simplify the sine x cos x. I'm there, but I'm not entirely there. And I think you're saying we could probably do a double angle. Just remember your double angle formula is 2 sine x cos x. So we would have to introduce a 2 there, which isn't, I mean, we can, there's nothing wrong with that. But just bear in mind that you might have to add that 2 in order to introduce that double angle. Okay, so factorization, awesome. We can take out that common factor of cos squared x, leaving us with cos squared x plus sine squared x. Now, immediately, grade 12, something should be going off in your head saying, I know what that is. I can do something with that. And when I say that, I mean this bracket that we have just gotten. So this bad boy over here, something in your head should be saying, I know what I can do with that. So what can you do with that? Nice, Camilo. Okay. Remember, guys, this is your squared identity. And just for the sake of this conversation, because these two identities are not given to you on your formula sheet, please remember that sine squared plus cos squared is equal to 1. And you have manipulations of this formula. So you could say that 1 minus sine squared theta is equal to cos squared theta. Obviously, I've drawn my arrows really badly. But you could also manipulate this to say 1 minus cos squared theta is equal to sine squared theta. So this is not given to you on your formula sheet. This is an identity that you need to know. Second one that's not given to you rather, is that tan theta is equal to sine theta over cos theta. You can obviously manipulate this and have like tan times cos equals sine, etc., etc. But the one thing I do want to point out with this one is that this translates to squareds as well. So tan squared theta is equal to sine squared theta over cos theta. And it also applies to double angles. So tan 2 theta is equal to sine 2 theta over cos 2 theta. I will obviously move that up. All right, so these two identities are not given to you on your formula sheet. You need to know them. All of your other formulae are obviously there on your formula sheet. So as Camilo said, that numerator's bracket simplifies to 1. So you actually just have cos squared x over 1 plus sine x. And now what? Because that's great. But what I want, and this is another sort of important takeaway, guys, always go back and look at what you're trying to prove. We're trying to prove that this is equal to 1 minus sine x. I've still got a cos squared x and I've got a sine x in my denominator. So how am I going to make that equal 1 minus sine x? And I'll give you a hint. I've just spoken about some identities that might be useful for us. Ramilo's got it. I'm going to give everyone another chance to have a think. Okay, nice, guys. So one thing I just want to point out is that this is kind of like a tan identity, but what I want you to be careful of is the fact that tan is sine over cos. Here I've got cos over 1 plus sine. So I've got a problem with the fact that it's cos squared. If it was cos squared over sine squared, then maybe we could introduce a tan, but you've got a squared and you've just got a sine. So that's a problem. The second thing that's a problem is it's 1 plus. Okay, so 1 plus, there's automatically another term there that I don't want. Tan is a single term divided by a single term. So just be careful when using tan. It's generally you changing the tan to sine over cos, especially in identities. But what we can do here is we can change that cos squared according to the identity that I just wrote down over here, which I'm going to highlight for you now. So we can use this identity that I wrote down over here, the fact that cos squared is equal to 1 minus sine squared. Now, the reason that's useful for me is because by introducing 1 minus sine squared, I achieve two things. Number one is that I now only have sines on my left-hand side. And that's good because in terms of what I'm trying to prove, there's only a sine ratio there. There's no other ratio. So I do kind of want everything in terms of sine. The second thing that this is helpful for is that I'm introducing the difference of squares. And the bracket in my denominator is one of those brackets that will then be created when I factorize. It's supposed to be an equals. Okay, so 1 minus sine squared x over 1 plus sine x. So this is dots. Dots is going to factorize to 1 minus sine x, 1 plus sine x, and automatically what I need you to see is the fact that you have now got the bracket that you want. So remember what we wanted was this 1 minus sine x. I now have that on my left-hand side. And Even better, the 1 plus sine x divides away with the 1 plus sine x. And so all we're left with here is 1 minus sine x. And so we can now make the statement that our left is equal to our right-hand side. Okay, so when proving identities, you always need to be looking back to what it is that you want. And you need to sort of ask yourself, am I achieving this goal? So earlier I said, us changing to the 1 minus sine squared is a good thing because now I only have sines. I knew that I only wanted sines because on my right-hand side, I only had a sine ratio. Introducing coses and tans is going to be a problem for me because I'm going to eventually have to get rid of them anyway. So let's not introduce something that I'm going to have to get rid of anyways. We need to always go back to our identities and our formulas. So like I say, these two green ones that I've put on the right-hand side, those are not on your formula sheet. You need to know them. And as you can see, you need to know the manipulations of them. So when I say the manipulations, I mean the things that are in the arrows. So everything in yellow here. You need to know both the original identity as well as their manipulations. All right, and especially the squared identity. These manipulations, we do use a fair amount. Okay, there's a question. Sorry, I'm going to have to read it out loud, otherwise my brain doesn't compute. Ma'am, when are we allowed to cancel if there's 2 coses or 2 sines? For example, are we allowed to cancel 2 cos squared x in the first line? So just be careful. You can only cancel things that are in the numerator and in the denominator. So if this first line had been maybe cos squared x and then your bracket over a cos squared x, then yes, you can cancel those 2 things because there's a single term in your denominator and you factorize the numerator. We can't cancel anything in what we have written down because there's nothing that's dividing top and bottom, allowing us to essentially divide them away. You can also only start canceling once everything is either multiplication or division. So what I mean by that is, at this point here, everything was either multiplication or division. Inside my bracket, I had a plus or minus, absolutely, but it is still the cos squared times a bracket. You can cancel out the whole bracket. You cannot cancel out individual terms. So what I mean by that is you can't say, okay, cool, sine x divided by one of those sine x's. No. You never, ever, ever divide or cancel out between terms, but you can divide or cancel out between factors. So once everything is multiplied or divided. I hope that makes sense. If it doesn't, just let me know. Cool. Okay. So often in identity questions, we will ask you to prove an identity, and then we move on to maybe something like, hence determine the value of this expression, and then you could use your identity. I'll give you an example of that in a second. Or like in this next question, asking you where, for what values of x in the interval x element 0 to 360 is that whole beautiful fraction undefined. Okay, so this is one of the ways we sort of extend the identity question, asking you where is it undefined. So my first question, guys, is what does it mean for a fraction to be undefined? So what does this actually mean? And Sile?
It means that the numerator must be 0, or the top number must be equal to 0.
Oh, hang on, Canicelia. Sorry, you're so soft, and I think that's my fault. Okay, sorry, go again.
And I was saying it means the top number must be equal to 0.
Okay, close. The denominator must be equal to 0. Okay, so guys, remember, this means that our denominator, is equal to 0. If we have 0 over x, that's fine. I've got no problem with that because 0 divided by anything is still 0. What I don't want is a value divided by 0 because that is undefined. So because the question is asking us where is it undefined, all we want to do here is basically set up an equation where my denominator is equal to 0. So all I want to do here is say 1 plus sine x is equal to 0. Because if that denominator is equal to 0, my identity is undefined. Nice, guys. I see that on the chat as well, that you guys are saying denominator equals 0. That's perfect. Right, there's a question, will they ever say undefined without a fraction? They could. What would then be there would be a tan. So it might be like, I don't know, tan plus sine squared. I don't know, I'm making nonsense up. But if it's just an expression and I'm asking you for where it's undefined, there'll be a tan there. And what we need to remember is, again, our identity. Tan is equal, because apparently that's an equal sign. Tan is equal to sine over cos. So when that's the case, what you want to do is you want to say cos is equal to 0 and then solve your equation. Because if tan is present, we need to remember that it is actually a fraction, and so we can then still apply denominator should equal to 0. All right, but in this case, we've got 1 plus sine x equals 0. It's just a basic equation that we need to go and solve. This is going to be quite a nice one because there's special angles. We'll come back to that interval in a second. Let's deal with this. I'm also fully aware that I did not do the mark allocation for the identity. I'll go back and do it now. So this would be sine x is equal to -1. Remember, when solving a general equation, you need to find a reference angle. To find a reference angle, what you do is you say shift sign of just the ratio without the sign. So here we would say shift sign of 1. The sign we will use in a second. And shift sign of 1 is 90 degrees. Okay, the sign of your ratio, so that negative, tells us the quadrants that we're working in. So because sign is negative, we're working in quadrants 3 and quadrants 4. And we are then able to get our two solutions. So in quadrant 3, remember you apply your reduction. So x is equal to 180 plus 90 plus k times 360. And so x is equal to 270 degrees plus k times 360. In quadrant 4, you have got x is equal to 360 minus 90 plus k times 360. Getting my integer. And 360 minus 90 is also equal to 270 degrees. So what actually ends up happening here is that you get the same solution. So you do not have to do it twice. If you realize that you're going to get the same solution, don't do it twice. There's no point in that. You can, but you don't have to. And now we're going to go back to that interval that was given to us. So the interval that was given to us said that x is an element of 0 to 360 degrees. So I only want the solutions in the first 360. And this is now where your general solution comes into play. What you basically do is you say x equals, and you start adding that k times 360. So you either add 360 or subtract 360 from this answer that you've gotten until you no longer fit inside the range. Now, in this case, if I said 270 plus 360, I'm getting 630, which is way, way outside my range of 0 to 360. So I can ignore that. If I said 270 minus 360, I get negative 90, also not in the range. I want from 0 to 360. So actually the only solution that is valid here is 270 degrees. All right, so that is one of the ways that we can ask an identity question, like an extension of. Another way that we could ask you this, and again, I'll do the mark allocation in a second. I just want to show you the other way that we could ask you something like this, is I could say, you've proven the identity, and the next question could then say hence. So I could say hence determine the value of cos to the power 4 45 plus sine squared 45 cos squared 45 over 1, whoops, that's an aggressive one, 1 plus sine 45. I'm going to move this to be where it needs to be. Things are just not working for me today. So I could then ask you to find the value of this expression. Now, what you would need to note here, what you need to sort of realize is the fact that this fraction that I've just written out is exactly the same as the left-hand side of my identity. In the previous question, you had just proven that this identity was equal to 1 minus sine x. So all you do here is say 1 minus sine of 45 degrees, which is a special angle, and you go and calculate the value. So that's another way that this question can be asked, hence determine the value of. And what you need to remember is that anytime we say hence, use the answer that you've just gotten. What you've just established or what you've just worked out is going to be useful in this next question. Okay, so that's the two ways we ask it. Either way is an undefined or hence determine the value of, and look out for special angles like this one, double angles, all of those sorts of things if it's a hence question. Right, quickly mark allocation, because obviously I'm getting very excited about trig and that's not forefront of my mind. Mark allocation for your proving identity. Again, obviously the mark will be allocated in a different place depending on how you have proven the identity. In terms of how we have proven the identity, it would be that factorization step right at the start. So factorizing appropriately. Understanding that cos squared x plus sine squared x is 1, so leaving you with just a cos squared x in your numerator. Understanding that you needed to apply the square identity to say 1 minus sine squared x, and then factorizing appropriately to eventually get your left-hand side equals right-hand side. In terms of the question that we've just done in terms of where is it undefined, generally speaking, grade 12s, these equations are very nice and easy. I'm not saying that there will always be special angles, but because it's equal to 0, it kind of is. All right. So in this case, it was only 2 marks, so nothing super tricky. And because the solutions ended up being the same, we're not going to double up a mark for a solution. So you're going to get a mark for understanding that you should make it equal to 0. And then in this case, because it was specific range we gave you, you're going to get a mark for only saying 270 degrees. So not a lot of marks. It's not very generous by any shape, sense, or form. But it's understanding that undefined means making your denominator equal to 0 and then getting the appropriate solution for that. Okay, I know there's another question here, but there's a fair amount that I've written down. So let's take a screenshot thus far, and then we'll move on to the third identity question that we have here. Now, the third identity question here is definitely a complex. I won't maybe go as far as to say it's problem solving, but it's definitely a complex question. Again, grade 12s, if you've got questions, please ask. I know I'm sort of going through this at a pace, but we obviously need to get through stuff. Okay. So the next question in the identity search is asking us to write down the minimum value of the function defined by a y equals cos to the power 4x plus sine squared x cos squared x over 1 plus sine x. Now again, this is 5.2.3. We proved an identity, we showed where it was undefined, and now we've been asked this. Because we have already proven a whole bunch of things, what I want you to remember is that this y equals this beautiful thing, and it's referring to a function, so a graph. I can't even begin to visualize what that graph would look like. There's cos to the power 4, there's sine squared, no, like absolutely not. But I have already proven this identity is equal to 1 minus sine squared x. So we already know that this is equal to 1 minus sine x. You've proven the identity. So there's no need to work with that horrible regurgitation over there. We can just work with what we already know and something so simple. So what I want to do here is I just want to put this in a better form for myself to imagine the function. So y is equal to minus sine x plus 1. Now, when I say a better form to understand the function, you need to go back to your trig functions. So for a sine function, y is equal to a sine bx minus p plus q. It looks horrible. I'm fully aware of that fact, but generally speaking, we put the sign or the ratio first, and then we put the constant. So that's all I've done here. Okay, A, remember, is your amplitude, so it stretches the graph vertically. B in front of the X changes the period, so it either squishes the graph and makes it like cycle much faster, or it expands the graph and pulls out how quickly my cycle occurs. That minus P shifts my graph left and right, and the Q shifts my graph up and down. Okay, I do have a summary of trig graphs, which I'll pop up on the classroom as well for you guys, but that's just a very quick, there you go. I feel like some questions just came through on the chat, but I'm not there. Okay, so question, please explain the first step. I'm assuming you mean this is the first step. Okay, so guys, listen up. You have already proven that this identity is equal to 1 minus sine x. You've already done that in 5.2.1. So rather than trying to figure out a function or what the graph would look like of cos to the power 4x plus sine squared x, cos squared x divided by 1 plus sine x, you know that this is exactly the same thing as 1 minus sine x. Because you know it's exactly the same thing, we can just write that equation or write that function as y equals 1 minus sine x. So there's no need to go and work with that complex fraction because you have already proven that it is the same thing as 1 minus sine x. Now that we know it's the same thing as 1 minus sine x, we can start to visualize this as a function. So all I've done is I've changed my order because I want to know what my amplitude is, so the a sine x, and in this case, what the shift up or down is, the q value. And so this is where your knowledge of trig graphs is very, very important. All right, before I carry on, is everyone understanding why I've done what I've done? So do we understand the first step? Do we understand what I've done? Cool. Okay. So now that we've got that, now guys, there's a few different ways to do this, but honestly, the easiest way is to visualize a trig function. So I cannot stress how important it is that you can understand your basic trig functions and the manipulations thereof. So what I mean by that is a basic trig function. So the basic sine function. Okay, it's not going to be the most beautiful sine function I've ever drawn in my whole entire life, but we're going to just work with it. Looks like that. For the first three, that's actually a pretty damn good sine graph. I'm pretty proud of that. Anyways, for the first 360 degrees, this is what sine looks like. So it starts at 0. It has a maximum at 190, an intercept with the x-axis at 180, a minimum at -1 at 270, and then another x-intercept at 360. Like I say, I would know that. Your basic trig functions, you should know what the basic or parent function is. Now we can go and see what has happened to our function according to my question. So remember, I'm now looking at this situation. So the first thing that happened is that a became negative. Remember, when that a becomes negative, your graph flips. So the negative is creating a sine graph that now looks like that. And the +1 means that my graph is moving up 1 unit. So this whole graph moves up 1 unit. It's great that I have a computer, I can just move it, but it just shifts up 1 unit. So I'm going to do that again, and how I knew it sat there. Remember, this is a minimum at -1, this is a maximum at 1. If I'm going 1 unit up, that minimum now moves to 0. And that maximum now moves to 2. And the question said, write down the minimum value. Well, my minimum value is 0. because I shifted from -1 up to my x-axis. So the minimum value of my function here is 0. Right, again, this is a complex question. I won't go far as problem solving, but it is a complex question. It is not supposed to be an easy question, but what I want you guys to remember is that if you've proven an identity, you know the simplified form of that expression. When I'm referring to a function, knowing your parent graphs is so important. And like I said, I'm pretty sure I have a summary somewhere. I will find it and I will upload it onto Google Classroom. But understanding what's happening to your graph in terms of shifts, stretches, amplitude changes, so on, is so useful to you, not only in identity type questions or equation type questions, but when you actually get to trig functions as well, understanding what's going on. Okay, so that's how we would find the minimum here. Remember that you have actually proven that it's equal to something much simpler. So work with the something much simpler. Right, I'm going to stop here for you guys to take a screenshot because then we move on to 5.3. And if you've got questions, obviously, please ask. Again, that is not supposed to be an easy question, right? That's not supposed to be something like, oh, cool, 2 marks, I got it. It's supposed to be tricky. Just so that you understand where your marks would come from. In this case, it's actually just a mark for your answer because you don't actually need to show any working out. Obviously, you can do what I've done here and you can draw the graph to visualize it. For me, that's very helpful to visualize what's happening, but there's no working out that we can allocate marks to. So it's just 0. I mean, yes, you get 2 marks for saying the minimum is 0. Sorry, that's what I meant. Tumelo?
Ma'am, is it possible to work this out without visualizing it?
Yes, I mean, there must be other ways to do it. So your minimum value would be where x is equal to 0. So if you just substituted in 0 degrees, no, that's not going to work. You still get a y value of 1. Oh, wait, sorry, I'm being a bit silly here. So yes, there are other ways to do it. I was just being a bit of an honor. Another way that you can do it, and you still sort of have to know your basic parent function, but another way to do it is to know that once you flip the graph, this minimum is at 90 degrees. So I'll just take my graph back before it shift. So if I take that graph back down, this minimum occurs at 90 degrees. And like a normal graph maxes at 90, but now because of the flip, the minimum is at 90 degrees. So what you could do is you could say y is equal to 1 minus sine of 90 degrees, and you could substitute in the x value where you know the minimum will occur, and that gives you 0 because sine of 90 is 1. So you would have 1 minus 1, which equals a minimum of 0. So you could use substitution, but again, it still relies on you understanding the basics of your parent sine function. But you could do that, yeah. I'm gonna be honest, I would have never thought to do that because I visualize it. But yes, absolutely. Okay, cool. So let's have a look at this one. Now, guys, this is technically something that we expect you to know. It's basically proving your compound angle formulae. Most of your textbooks do show you how to do this, but I'm just going to give you the hint to sort of remember it by, and you go from there. I will do the proofs, find the proofs for you, and I'll upload it as well onto the Bootcamp classroom, and I'll actually put it on our main classroom as well, especially for those of you who are in both. But we expect you to know the proofs of compound angle formulae. Now, It's not hard by any stretch of the imagination, but you already have to learn so many proofs for geometry. Learning other proofs is just, it's time consuming. So that's why I'm saying, I would not learn them off by heart. I would just think of the hint or the key thing that needs to happen in order for you to prove it. Okay, so like I said, this was asked last year, so they expected them to know this proof of your compound angle formulae for sine A minus B, but don't learn it off by heart. Okay, so the hint here, or the thing to take away from this, is your use of co-ratios. So co-ratios is going to be very, very important here. Now let's read the question. So it says, given cos A minus B is equal to cos A plus B plus sine A plus sine A sine B. We know that's true. That's on the formula sheet, we know that. It's saying use the above identity to deduce that sine A minus B is equal to sine A cos B cos A sine B. Now, automatically, you should be thinking, well, no, thank you. But you should also be thinking, how on earth do I get from a cos to a sine cos? How do I get from a sine to a cos sine? And that is where the co-ratios come in. We know that if we want to change from a cos to a sine or vice versa, we have to use a co-ratio. Right, now, which angle you choose to apply your co-ratio to is completely up to you. I always just go the first one, like for me it's easier, but it really makes no difference. Okay, so remember, we have been told that we need to use this identity. So we're not using anything that we've been given just yet. We're not going to use anything over here. We're going to use what we've actually been given. So we know already, based on what we've been given, that we are wanting to work with, or we're wanting to prove that sine A minus B is equal to that whole thing. That we were given a cos situation. Okay, that's not a problem. If I go back to, I need to work with cos, the way I get cos, no, sorry, let me reword my words. The way I get the sine from a cos is to say cos 90 minus. Cos 90 minus will produce the sine that I'm wanting. So, cos, that's not C, let's try that again, no. Cos of 90 minus that angle A minus B will eventually become that. So think about this again. Cos 90 minus an angle becomes sine of that angle. If I said cos of 90 minus this A minus B, the angle, I'm going to eventually simplify to sine A minus B. So by applying that co-ratio, this co-ratio, I'm actually creating the sine that I want. Right, so we've got cos of 90 minus A minus B. And now we're basically just going to start simplifying the situation. So we can distribute the negative in. So I've got 90 minus A plus B. And now remember, you're working with compound angles. So you need to have two angles to work with. Compound angles is an angle plus an angle minus an angle. So the first angle that I'm going to work with is the 90 minus A. The second angle that I'm going to work with is the plus B. So if I now expand this according to the expansion I was already given, because remember, we have to use what we were given, I know this will be cos of 90 minus A times cos of B plus sine of 90 minus A times sine of angle B. And now I'm going to start simplifying. Remember co-ratios. Cos 90 minus becomes sine A cos B. Plus sine 90 minus becomes cos A sine B. And if you go and have a look at what it is you wanted to prove, good gracious me, we wanted to prove sine A minus B is equal to sine A cos B minus cos A sine B. That's exactly what we've proven, right? We took that sine A minus B, we applied it, we turned it into a co-ratio in terms of cos that we could use, and we've gone and proven that it is in fact sine A cos B minus cos A sine B. Right, not a particularly hard thing to do. It's just co-ratios and applying your compound angle formulae. And like I say there, you can go and learn exactly how to do this. So if you want to learn this step by step, you can. And like I said, I'll put it on the classroom for you if you want to go and learn it. But you already have to know your Euclidean geometry proofs, of which there's 6, 7 of them, including prop theorem and midpoint theorem. So you already have a lot of proofs that you need to know for paper 2. This is just co-ratios, something that you have been doing since grade 10, grade 11. So it's nothing new, it's just applying a co-ratio. You can also see it's only for 3 marks, right? So if you're going to just abandon those 3 marks, that's fine. And then next question says hence or otherwise, you're just going to use what you've already been given. So you abandon 3 marks to get 5 marks, rather 5 marks than 8 marks that you sacrifice. All right, so again, you can just go and learn this. I'll put it up on the classroom for you. Like I say, personally, I don't know what the proofs are by heart. I just know I need to use co-ratios and I apply that accordingly. Right, so anytime you are then given, such as in the next question, hence or otherwise determine, it's telling you use what you've just worked out. It's telling you that what you have just done is going to be useful for you. So look back at what you have. Determine the general solution of the equation sine 48 cos x minus cos 48 sine x equals cos 2x. So we're solving an equation here. Okay, this is the situation I'm not so keen on, but this situation is equal to sine A minus B. We have just proven that. So what we can now go do, it's sort of like the identity thing. If we know it's equal to that, let's use the simpler version. So we can now write this as sine 48 minus x is equal to cos 2x. That is already a much easier equation to be working with. And now we have to start thinking about our general solution. So one thing that we need to bear in mind with general solution is the fact that when you have different ratios, we need them to be the same. If you've got a sine of a specific angle and a cos of that exact same angle, you can create tan. But in this case, I've got 48 minus x as one angle and 2x is the other angle. They're 2 completely different angles. When it's sine and cos of 2 different angles, once again, we're going to have to use co-ratios. Now, which one you apply your co-ratio to is up to you. Personally, I would never apply the co-ratio to a compound angle just because there's more room for error. There's more room for error. And so I would apply a co-ratio to the cos 2x. So what I mean by that is I'm going to leave the sine 48 minus x because I don't have a problem with that. But cos 2x I can write as sine 90 minus 2x. That's the same thing. According to my co-ratio, that is exactly the same thing. There's no issue there. And now that my ratios are the same, I can now start to solve my equation. Now remember, when we are solving a trig equation, we need a reference angle. In this case, my reference angle, I always pick as the left-hand angle when there is a situation where I can't type shift sine onto my calculator. So my reference angle here is 90 minus 2x. And because sine is positive here, I'm working in quadrants 1 and 2. Okay, so quadrant 1 solution would be my angle 48 minus x is equal to the reference angle 90 minus 2x, and then the whole plus k times 360, blah, blah, blah. Quadrant 2 solution is now where we have to apply the reduction. So again, it's the angle 48 minus x is equal to, we now apply the reduction appropriate for quadrant 2, 180 minus my reference angle of 90 minus 2x, and then the plus k times 360, etc., etc. And now you just go and solve your 2 general solutions. So for quadrant 1, if I bring that negative 2x over, it becomes positive x, or positive 2x, and minus x plus 2x is then just x. I have to bring the 48 over, so I have to say 90 minus 48, which is 42. So x equals 42 plus k times 360. K is an integer. And then for quadrant 2, I again need to do a very similar thing, but I do need to distribute that negative first. So 180 minus 90 plus 2x. That's k times 360. 180 minus 90 is 90. So just bear that in mind. But if I bring that positive 2x over, I get a negative 3x now. On the right-hand side, I've got 180 minus 90, which is 90. Bring the 48 over minus 48, so 42. And so now in solving this equation, I need to divide everything by negative 3. So 42 divided by negative 3 is negative 14. K times 360 divided by negative 3 becomes minus k times 120. And so I've got my two solutions for that equation. I've got my two general solutions for this equation. All right, so general solution, you need a reference angle, you need to apply the appropriate reduction for the quadrant, and you need to remember that if you're going to divide, if x has a coefficient and you're going to divide every term by that, remember that your 360 is part of that. So I had to divide that 360 by negative 3. I can't forget about that. Right, but again, grade 12s, this is a hence or otherwise determined. If you could not do question 5.3.1, okay, sure, you lose 3 marks, but you can still use that information to get the other 5. So it's not impossible. You can still get marks. You just need to be smart about it. Don't panic because you can't get the first one. Move on to the second one. So just so you can see the co-ratio is the mark allocation. You get a mark for understanding co-ratio in 5.3.1. You get a mark for expanding your compound angle according to the rule that you have. You get a mark for applying the appropriate reductions or the appropriate co-ratios, so turning the cos 90 minus a into sine a. And through doing that, you essentially are getting the mark for your final answer. In the general solution question, you get a mark for taking that whole expanded form and understanding that you do already know that it's sine 48 minus x. So applying what you already know. You get a mark for applying the co-ratio that you would need to do in this case. You then get a mark for setting up both of your equations with appropriate mark, and then I put 2 ticks. A mark for setting up your equations with appropriate reductions where necessary. And then you get a mark for each of your general solutions set up appropriately. When I say appropriately, plus k360 elements integer, and the second solution where you had to essentially convert it or divide by the negative 3 to get the negative k120. So correctly solving for your general solution, essentially. All right, let me make this a touch smaller so you can screenshot this. Oops, there we go. Any questions again, guys, please ask. Right, but that is essentially your general trig. Okay, so when, actually it's not your general trig, we still have one more question, but we'll get to that. This is general trig. This in this paper, you'll see in a second, is 31 marks. So of those 50 marks, 31 of them are general trig. It's anywhere between 30 and 35. That's 60 to 70% of your trig questions is just compound angles, finding general solutions, proving identities, using the Cartesian plane. The next one is a simplifying expression. But all of that stuff is 60 to 70% of your trig questions. So we need to be able to do it. Okay. So 5.4, and there you go, 31 marks, is asking us, sorry, I just coughed in your ears, I do apologize. is asking us to simplify sine 3x plus sine x over cos 2x plus 1 to a single trig ratio. Okay, now there's a couple of things I wanted to highlight for us here in this journey we are about to embark on. Firstly, single trig ratio means that you should have sine, a cos, or a tan. That's it. The issue, maybe you might have a coefficient, your angle might be a double angle, something like that, but you want sine, cos, tan, one of those three. The next thing I want to draw your attention to is the fact that this is 6 marks. 1 mark is for your answer. 1. Those other 5 marks are coming from applying reductions, applying compound angles, applying double angles, the appropriate simplification, so maybe distribution or LCD or whatever the case is, depending on the question. 5 marks for applying knowledge that you know. 1 mark for the answer. So have a look at this and tell me what you think we can do here. So we've got sine 3x plus sine x over cos 2x plus 1. What can we do? And remember, there'll be a few different ways that you can go and simplify this. So we're going to potentially have different answers and different solutions to the problem. And again, you have the knowledge, double angles, compound angles. Think about that sort of stuff. Any ideas? Okay. Right, I know it's not always easy to figure out where to start. So let's have a look. You've got 3x, you've got x, and you've got 2x as the angles in this question. If you want to simplify this to a single trig ratio, those angles need to be the same. Because right now, it's not like you can just say sine 3x plus sine x is sine 4x. That's not the way it works. Okay, those are not like terms. So what we need to try and figure out is a way to try and make all of those angles equal to each other. So now again, guys, there's a couple different ways that you can do this. It's very much going to be your English. It's very much going to be dependent on what you see first. But in my mind, I'm thinking, okay, if I can try and make all of these angles the same, I can get that single trig ratio. Now, immediately, the 3x and the x, those could be written as compound angles. So if we think about 3x can be written as sine 2x plus x. And sine x could be written as sine 2x minus x. That already in my numerator is now the same angle. I'm only working with 2x's and x. in my denominator, I've got a 2x, that's a double angle. And generally, whenever I've got a cos double angle, I leave it because I don't yet know which one of the three formulas I'm going to apply. So I just leave it for now. I'll decide a bit later once I've simplified my numerator, which cos double angle formula I should apply. So in my numerator, these are all compound angles, so I can expand. So sine 2x cos x plus cos 2x sine x plus sine 2x cos x minus cos 2x sine x. Fully aware that that is not very nice. Okay, it's not very nice to look at, not very nice to deal with. But hopefully we're going to have some like terms that we can eventually cancel and simplify, and it's going to make our lives easy. So let's see what we have. We've got a sine 2x cos x plus a sine 2x cos x like terms. I have also got a cos 2x sine x minus cos 2x sine x. So what's actually going to happen is those become 0. They're gone. And so in my numerator, I'm now just left with 2 sine 2x cos x. And in my denominator, that cos 2x plus 1. Okay, I still need to deal with that denominator double angle. We're getting there. What I see though in my numerator is that I've got a sine double angle. So my sine double angle I can simplify. I've got 2, and now this expands to 2 sine x cos x times cos x, all still over that denominator. And in my numerator, I've now got 4 sine x cos squared x. Okay. So, whoops, that's not a square, that's a 2. Right, so now what I need to do is I need to decide how I'm going to deal with this denominator, because obviously I don't have a single trig ratio yet, and that's a bit problematic because that is exactly what the question asked me to do. Just move all of this up. So I still need to get that single trig ratio. So now I need to look at what I have in my numerator and try and match it up with what's going in my denominator to try and start cancelling some of these ratios. I've got a cos in both the numerator and the denominator. So that already to me should be saying, okay, well, maybe I can divide away the coses if I change that cos double angle. So I want to change this cos double angle to a double angle formula that only contains cos. So that would require me to change it to this 2 cos squared minus 1. If this thing would like to work. Let's actually just move over here. So my numerator is still 4 sine x cos squared x. But now my denominator, I'm going to change that cos double angle to 2 cos squared x minus 1 plus 1. I also automatically know this is a good thing because minus 1 plus 1 eliminates. So I've got 4 sine x cos squared x rather, over 2 cos squared x. Right, now in this fraction, I can start simplifying. The reason I can start simplifying, remember I said earlier, we can only start simplifying once everything is plus and minus. So what I have here is a cos squared x that divides away with cos squared x. 4 divides by 2 once, 2 divides into 2 once. So what I have done is I've gotten 2 sine x. I've simplified it to a single trig ratio, exactly as the question asked me to do. So guys, when we get questions like this, when we're wanting to simplify to a single trig ratio, which is generally what the instruction tells me to do, when you've got so much going on, you need to start by looking at the things that you know need to change. So I knew that those angles needed to change because none of them were the same. Only way to get a single trig ratio is to get your angles the same. I knew that I had to use compound angles for the 3x and the sine x because The only way for me to get angles that look the same is to then use compound angles. In the denominator, I had a 2x, that's a double angle, it's got a whole set of rules, but 3x and x don't. So if I can maybe create a 2x somewhere, then I can start applying rules that I know. Right, Primelo?
Ma'am, could you please explain where the cos x came from in the fourth step?
Fourth step, okay. Just make sure we're all on the same page. So 1, 2, 3. This step over here with the really badly drawn pink star.
Yes, ma'am.
And which cos x? The one outside the bracket or the one
Yes,
inside?
the one outside.
The one outside. Okay, cool. So remember that came from what I'd simplified to. So in the step before, I simplified with all of my like terms to 2 sine 2x cos x. That cos x is the cos x over here, because the sine 2x, let's give me the color. The sine 2x was the double angle that I expanded there. The 2 still remained the coefficient, and the cos x I didn't do anything with. So it still stayed cos x at the end, and then I multiplied everything in. Make more sense?
Thank you, ma'am.
Perfect. Okay, so guys, that's the thing. And honestly, I do this a lot with double angles, is especially the sine double angle. I know that it expands to 2 sine x cos x, but when there's a 2 coefficient that's already there, I get myself confused and I don't remember to write the coefficient of 2 there. I just leave it as 2 sines x cos x. So this little color coordination thing that I've done is actually quite useful, because it's making sure that everything I had in my previous step has been carried to my next step. Yes, with a manipulation with a double angle, but I haven't forgotten anything. Because like I say, often, like I know it's something I'm guilty of. I often forget if there's a coefficient of 2 and then the 2 sine x cos x, I forget to have both 2's there and I leave off one. So always double check that you've carried through or you've carried down every single factor or every single thing from the previous step. Obviously with manipulations of like here, the double angle, whatever, but make sure you're not leaving anything out. Okay, this was not a particularly easy simplification question. I think that if I hadn't done this previously, if I was looking at it for the first time, I would be thinking, sure, this is a lot, just because of how many manipulations you had to do. So the manipulation with the compound angles and so on. It's not the only way to do it. There are other ways to do it. But just remember that in a question like this, bulk of your marks are coming from those manipulations that I spoke about. So if you want to know the mark allocations for this, the first one would be understanding that you have to work with compound angles, doing the expansion with the appropriate compound angles that you've used, applying your cos double angle. I know we did it a bit later on, but applying your cos double angle, understanding that once you had simplified your numerator, you had a sine double angle that you needed to go and expand. So that's 4 of the 5 marks. Also, this is a 6-mark question. I'm just losing it a wee bit. So before the sine double angle would be simplifying to the 2 sine 2x cos x, then the sine double angle, and then the last mark is your answer mark. Okay, so all of those marks are coming from your simplification, and kind of sucks because if you can't do the simplification, then you're losing all those marks, but try, right? Like I said earlier, there's other ways to do this. Expand the compound angle. Expand the double angle. That's 2 of the 5 marks, 6 marks. I don't know why I keep saying 5. It's 2 of the 6 marks. With questions like this, if you don't know where to start, just pick something to start with. Because particularly with questions like this, because so many marks are allocated to the working out, the likelihood of you having just done something somewhere with a double angle, a compound angle, excuse me, a factorization or whatever applies, it's likely that it's going to be a mark somewhere. So you can see that all of the things we did, compound angle, expansion, double angles, blah, those were all marks. So just start somewhere. If you are really confused, maybe you don't get all 6, but you can get some of the marks by starting somewhere with something. Okay. So guys, I know this was a lot of trig for paper 2, but like I say, it's 30% of your paper. That is a pass, right? So trig, super important. Analytical, we're currently doing it in class. So I know we haven't covered analytical, which sucks, but I'm fully aware of it, but we are doing it in class. And remember, you still have one more bootcamp next week where we will do some Euclidean geometry. Okay, but really important for paper 2 is trig. So I'm really aware of the fact that it is 4 o'clock. So I will leave this on the screen in case you want to take screenshots. Remember, all of the memos, all of the past papers are there for you guys. And all of those things that I said I would upload on the classroom, I will do it. Just need to find all of that stuff. So I will do all of that for you. And then, like I say, next weekend is sort of a wrap up. So next week